So this is lesson 4 on exponents and logs, and we're getting to vocabulary that is new. Although if you're in Chemistry 20, you've been introduced to logs. Exponents and logs are inverses of one another. That's the work that we did in Unit 1, where we let y become x and then x become y and ended up resolving for y. We've got some examples of logs. Uh, log of 1,000, I can do that on my calculator, is equal to 3. Your calculator is default for a log base 10 setting. So log base 10 of 10 is 1. Log base 10 of 0.001 is 3. Why is that? The answers are actually the exponents of base 10. So 10 to the 3 is 1,000. 10 to the 1 is 10, and 10 to the minus 3 is 0.001. Question that I want you to think about as we get started: can you take the log of a negative? Probably good to review how to find the inverse. Remember, when we find the inverse, we switch x and y. So my first step would be x is equal to 2 to the y. But I actually don't have any skill to solve for y. I cannot solve for y right now. I cannot solve for y. I need some new skills. We've got two graphs to build, so your calculator is helpful for that. Can you please plot the graph of y equals 2x and then find the inverse by flipping your x and y as we're used to? It's good to go through the exercise of finding inverse. It's really easy to find inverse by flipping your x to your y and your y to your x. We can do that with the table of values. I've graphed that. Typical relationship between the graph of an exponential equation and its inverse, which is going to get new language. Let's turn the page over. So here we have the language being expressed to us. The log function is the inverse of an exponential function. So it has a special format. The graph of the log function is the same as the graph of the inverse notation that we were trying to communicate. So previously we were trying to communicate in this format, but now we actually have a way of getting the y out of the power position and out of the exponent position, and it's said to let's take the log. By taking the log base 2 of both sides, I get y on one side and then log base 2 of x on the other side. So that's how we're going to practice finding our inverses. It's a mathematical function that we will apply. The logarithmic function with base b has the following representation. The base can be anything, 3, 5, 10. Your calculator is defaulted for 2 logs, log base 10 and log base e. There's the argument of the logarithm, or the contents of the function, and then the value of the logarithm. Note what the policeman says: the arguments can never be negative. I cannot take the log of a negative argument. Just not possible, not defined. We've got two graphs, the two graphs drawn that we exercised on the previous page. So we're just going to turn the page over. Actually, there were some conclusions that we have to do. Domain range, x-intercepts, y-intercepts, all that good stuff, and asymptotes. Let's do that. So pretty typical for an inverse, if you can identify the domain, range, x-intercept, y-intercept, asymptote for the function, the inverse of that will have things flipped, x and y flip. So you should see a relationship between the domain of one function and the range of the other. The x-intercepts and y-intercepts flip their identification, and the asymptotes. Remember how we are getting to this state. We are exercising the log function. So I'm taking log base 2 of x to isolate the y. That's the function that's actually being exercised. Logs generate exponents. Can't say that enough at the start of our lesson. Logs generate exponents. So we're looking at the graph of y equals 2 to the power x, that same table of values we made, and its inverse. And just doing some discussing about the points. When I look at the graph of y equals 2 to the exponent x, when I have the first point in A, what's that telling me? It's telling me that 2 to the exponent negative 2 is equal to a quarter. Excuse my orientation. When I look at the log statement, then the statement is a little bit different. What's that telling me? It's telling me that the number 16 is a result of 2 to the power of 4. So 2 to the power of 4, 2 to the y value is equal to my x value. And we can do some translating down here, looking at my log statement. Um, 2 to what power is 4? Well, that's 2 to the 2. 2 to what power is 1? That's 1. 2 to what power is 1? Well, that's 0. That's the weird one. So in the exponential form, it's 2 squared is equal to 4. 2 to the power 1 is equal to 2. 2 to the power 0 is equal to 1. And I should be using the word exponent. 2 to the exponent. Watch our language. Logarithmic form. If I have the exponential form and I'm taking the log form, remember logs generate exponents. So log base 2 of an eighth is minus 3. Log base 2 of a quarter is minus 2. Log base 2 of a half is minus 1. And we already played around with log statements and powers of 10. We actually know that the log of 1000 is equal to 3 because of the statement that we have at the start of our lesson. There certainly is lots to remember about a logarithmic graph. Um, and you can use your calculator to help you remember this. I would graph a simple log graph, y equals log 10, or y equals log x. The x-intercept is 1. There will be no y-intercept. The y-axis is your vertical asymptote. Domain and range statements we've already played around with. The equivalency of the inverse statement to the exponent form. And b is the base of both the logarithmic function and the exponential function. Take a look at the policeman's notes, and we're going to try to play around with some statements. We have to answer in the form of y equals. So I've worked ahead just a little bit on this. First, I have to find the inverse. So in order to find the inverse, I flipped to exponential form, and then I made the x's and the y's flip spots. So this is the inverse of my log function. The next one, I had to find the inverse first. So the inverse is x equals 8 to the y, and then I have to answer in the form of, well, what is y? I need my log function for that. Take log base 8 of both sides. That's going to drop my y down. So log base 8 of x is equal to y. And we get some more practice of converting from logarithmic form to exponential form. Hopefully we're seeing what logs generate. Logs generate exponents. So that means 7 to the 4 is equal to x. And 5 to the y is equal to 15. This one, b, not bt, because that's my base hiding there. T to the m is equal to b. And then I've got a weird one. I need to get that in the same format. Please watch my b's and sixes. They look remarkably the same. This would be b to the exponent 5/4. So b to the exponent 5/4 is equal to 6. I'll do a couple of these into exponential to logarithmic form. So log base 4 of 64 is equal to 3. We're generating the answer. We're generating the exponent position. So the log base 2 of 1/8 is minus 3. The last one, the log base a of 2x plus 4 in brackets is equal to 5. And just a little bit more. Track this one. This says that x to the power of 3, no, that's not what it says. It says 2 to the power of 3. 2 to the power of 3 is equal to x. So that means x is equal to 8. And now I'm using that value next door. Log base 2 of t is equal to what x was, which is 8. So now this says 2 to the 8 is equal to t. Well, what's t? And t would be 256. We'll fool around with that one other kind of example. So we want to isolate the exponent. So we want to go y over 2 is equal to 3x, and then convert to log form. So then the log base 3 of y over 2 would be equal to my x. Or the last one, which has a 2/3 on the right hand side, it'll be a 3 over 2 on the left hand side, 10x. So then the log base 10 of 3 over 2y would be equal to x. And here we're getting 7 to the power of x equals y over 3. Solve for y. The 3 moves up to the other side. 3 times 7 to the power x is equal to y. And I'll try the C one. That says 5 to the power of x is equal to 7y. If I solve for y, y is 1/7 5 to the power of x. So I managed to squeeze that into under 15 minutes with people coming in and out. That's lesson 4, moving between logs and exponents, and that'll be enough for Tuesday's work.